Hi everyone, today we're going to learn about energy and the first law of thermodynamics. Relating to the learning objectives from College Board, that the student is able to interpret observations in a reaction to generate relevant symbolic or graphical representation of energy change. That student can generate explanations regarding the transfer of thermal energy between systems as a result of molecular collisions. The student is able to use conservation of energy to relate the magnitude of the energy change occurring in two or more interacting systems, including identification of the system, the type, or the direction of energy flow. The law of conservation of energy states that energy can be converted from one form to another, but can be neither created nor destroyed. There are two common forms of energy in chemistry. They are kinetic energy, which is energy of motion, and potential energy, which is energy stored in chemical bonds. Energy is the capacity to do work or transfer heat. Thermal energy is a form of kinetic energy associated with motion, and the energy is associated with the object's temperature. That's a measure of the average kinetic energy of the particles at random motion resulting in molecular collisions. Thermal energy transfers heat between objects at different temperatures from a hot to a cold object. Chemical energy is a form of potential energy. It's energy associated with the position of electrons and the nuclei. It's energy stored in a chemical bond that arises from the Coulombic attraction between protons and electrons. The first law of thermodynamics says that total energy in the universe is constant. Now, the universe is made up of system and the surroundings. The system is defined as where all the substances are undergoing either a physical or chemical change. The surroundings include everything outside of the reaction, such as the container, the lab bench, air, etc. We must understand that the energy is transferred from one into another. So if energy is lost by the system, energy will be gained by the surroundings and vice versa. Internal energy change, delta E. It is the sum of the kinetic and potential energies of all the particles that make up the system. It is a state function. In other words, it is independent of the pathway, but depending on the initial and final state. Internal energy change is equal to thermal energy, heat, and work. The signs of these are very important. It will be very helpful for you to truly understand the signs in this chart. When heat energy is entering the system or gained, it is positive. When heat energy is released into the surrounding, it is negative. When work is done to compress the system from the surrounding, it is positive work. But when work is done by the system, and the gas is expanding, this is negative work. The delta E, when energy flows into the system, is positive, and when energy flows out of the system is negative delta E. So here's a diagram. If the energy is flowing from the system into the surrounding, this is exothermic, delta E is negative. Or when the energy is flowing from the surroundings into the system, this delta E is positive, endothermic. The units of energy arising from kinetic energy, 1/2 mv squared, where m is the mass in kilogram, v is velocity in meter per second. So energy unit is defined in joule, where 1 joule is 1 kilogram times meter per second squared. Relating joule to calorie that we are quite familiar with, 4.184 joule is 1 calorie. 1 calorie is the heat required to raise 1 gram of water by 1 degree C. And 1,000 calories is equal to 1 kilocal, which is equal to 1 capital cal. Now this 1 big cal refers to foot calorie. Work is equal to minus P delta V. When there's an increase in number of gas molecules, the volume of the system is expanding and work is done by the system against constant pressure. We define that as negative work. So here you look at the diagram, initial state, which is a smaller volume, final state, larger volume. And there's an increase in the volume, and this work is done by the system on the surrounding, negative work. However, in the reverse situation, if there's a decrease in gas volume, that means volume contracts and work is done by the surrounding on the system, this work is defined as positive. Delta V, change in volume, is equal to final volume minus initial volume. Notice that work has the same magnitude as P delta V, but it is opposite in sign. And to convert from P times delta V, we have a unit of liter times atmospheric pressure. 1 of that is equal to 101.3 joules. Try practice problem number 1. The volume of gas increases from 10 to 15 liters at constant pressure of 2.5 atm, and the system releases 4.8 kilojoule of heat to the surrounding. Calculate the change in internal energy. Work is equal to minus P delta V, or negative 2.5 atm times final volume 15 minus initial volume 10 liters. So that will yield negative 13 atm times liter. Now this is converted into joules, and we have negative 1,300 joules or minus 1.3 kilojoule. The work is done by the system on the surrounding in expanding. The heat flows from the system to the surrounding because it's releasing heat from the system. So the heat is in negative term, negative 4.8 kilojoule of heat plus negative 1.3 kilojoule of work equal to negative 6.1 kilojoule of change in internal energy. Try practice problem number 2. Predict the sign for Q and W when water vapor condenses to form water liquid. Here's the equation. Condensation is an exothermic reaction in which heat is released by the system flowing into the surrounding. Therefore, Q is negative. The volume of the system actually decreases as liquid molecules are closer together than gas molecules. So the system contracts in volume. Work is done by the surrounding on the system. Therefore, work is positive. Practice problem number 3. For the following reactions at constant external pressure, is the work done by the system or by the surroundings? When tin metal reacting with 2 moles of chlorine gas to form tin tetrachloride solid, the work is positive because we have 2 moles of gas reactant decreasing into 0 moles of gas product. So the volume is decreasing and work is positive because now the work is done by the surrounding on the system. The next one. We have 2 moles of ammonia endothermically absorbing heat to form nitrogen and 3 moles of hydrogen. Now, we're going from 2 moles of gas reactant to form 4 moles of gas product. So the volume is expanding from the system and against the surrounding. We define that as negative work. In mixing silver nitrate and potassium iodide aqueous solution, the silver iodide precipitate is formed and potassium nitrate aqueous solution. And in this case, there's no change in the volume at all. Therefore, the work is negligible. To sum up what we have learned today, we learned 2 common forms of energy in chemistry, and they are the kinetic energy, which is thermal energy, and potential energy, which is chemical energy. We learned that energy in the universe is conserved and transferred between the system and the surroundings. We related the sign of change in internal energy, heat, which is Q, and work, which is W, to the direction of energy flow. We explained and predicted the transfer of thermal energy and work done by the system or by the surroundings associated with the reaction. And finally, we quantified the magnitude of delta E in terms of Q and W. I hope that you have found this video helpful. If you like it, please give us a like, and I look forward to seeing you in the next part of this topic.